Alrighty. I'm gonna go this way. Okay. So last week we had started our unit on systems. Last week we learned a system of equations is
A system of equation is
or what does it look like?
it's multiple equations.
Yeah.
Yeah.
Multiple equations. I think we had more to the definition, multiple equations with the same variables, the same solution points, but it looks like multiple equations. We had started talking about how you solve systems of equations last week. Last week we were solving by graphing, and last week I had kind of hinted at the fact that there's more than one way to solve these systems. One way is graphing. There are two other ways you can solve systems, and those are the two things we're looking at this week. So the way we're looking at today is by substitution. You know the word substitution. What is substitution?
Replacing something with something else.
Yep. So substitution is this idea of replacing something. That's going to be helpful to know, since what we're doing today is going to involve that. So this part right here just kind of summarizes what we were saying. We said there's more than one way to solve systems of equations. The first way, the way we learned last week, was by
Graph.
Yep. I don't know if I want this marker. Graphing. And then the second way, the way we're learning today, is substitution. After we've gone through all three methods, we're going to spend a day focusing really in on why do we have three different ways to solve the same thing. There are situations where one way is going to be easier than another. The reason we brought it up last week was because we were talking about, like, with graphing, you have to have a graph. So if you don't have a graph, then what we're doing today might be an easier way to do it. So when it comes to substitution, you had already said that substitution is this idea of replacing one thing for another thing. I've got this system right here, and we are going to solve this system by using substitution. Now you might have noticed this system here, does it look familiar? So the one you were just doing, and you already were talking about substituting. If I look at this system, you would notice we've got y equals -4. And so you had mentioned earlier, well, I see y equals -4. What could we do with that?
Replace plus y with -4.
Yep.
Or -4.
Yep, you got it. So I can substitute this equation into the second equation in our system, and that would give us 2x. I could say plus -4, or just -4 equals -2. Now when we substitute, we end up with this equation right here. What do you think we want to do with that equation?
Get the 2x by itself.
Yep, solve for x. So if we want this by itself, what's the first thing I'm going to do?
You add 4 on both sides.
Yeah. We add 4 on both sides. That will cancel out our 4. So we get 2x equals
2.
And then our last step.
Divide both sides by 2.
Sounds like a plan. And that'll leave us x equals 1. Now remember what we're doing here. We're solving a system of equations. And last week, when we were solving differently, at the end we were always finding the solution looks like what? Our answer for these always looks like, I see you doing it with your hands.
A point?
Yeah, a point, a coordinate. What I saw you doing with your hands is there's two numbers involved, right? There's an x coordinate and a y coordinate. We figured out x. A lot of times people want to stop, say x equals 1. That's the answer. I'm done. But it goes back to what we learned last week. When you're talking about a system, the answer looks like a point. So I've got x is 1. What about y?
Well, y already equals -4.
Yep.
So the y is -4.
Agreed. That right there, this method that we just did, is what substitution looks like. In order to use substitution to solve, we're going to need one of our equations to say x equals or y equals. In this system here, we already had the y equals -4. If you're using substitution, you're substituting one equation into the other equation and then solving that new equation to get your answer. Now this one was nice because it already said y equals -4. Do you think all equations are going to look like that? No, of course not. That's just where we're starting. Questions on what we did here? Okay. There is one on the back of that paper that looks like this, similar to the one you just did with me. Do you want to try this one?
Okay.
Oh, you want to try it on the board? You can do it on the board, on your paper.
I'll do it on my paper.
Okay. Denise, do you want me to check you?
Which one? I'm sorry.
Now, Denise, what's that final answer always look like for a system of equations?
Oh, thank you.
Beautiful. And I remember to. No, I don't. Oh, check at the very end. Check your math. 30 divided by 3.
Wouldn't it be -30?
Yeah, or -30 divided by 3. But the mistake is with the 30 divided by 3. How many 3? There you go. Yep.
Okay.
So the same thing I said to Denise, what's that final answer look like when we're solving a system?
The point.
Mhm.
That would be
Yep, beautiful. Now you've got that big box off to the side. We'll do that part together. You figured out that the solution point is for -10?
yeah.
And on your paper, you've got a little space over here that says check. This also goes back to something we learned last week. If we've got a solution point and we want to check to make sure that this is the solution for the system, what could I do?
You could put the x and y for -10 into the x and y in the equation.
And which equation?
The second one. Or the 5x plus 3y equals -10. So
Why not this one?
Because that is just, there's no y.
Could you still substitute in the first one?
Yes.
Mm-hmm.
And it would still be correct.
Yeah. You do want to check both of them. This one is very easy to check. We can see that 4 equals 4 right away. If there was more to the equation, though, we would want to substitute in both. But what you're saying is we're going to take both of these numbers and substitute it for both of the variables. And what are we looking for?
If once you put it in, the math is just correct.
Yeah. If you end up getting something true, like 4 equals 4, -10 equals -10, something like that. So let's do that. When we do that, what is it going to look like?
So it would be 20 plus -30
And I'm going to.
equals -10.
Where's the 20 coming from?
5, and then the x is 4, so it'd be 5 times 4.
Yep. So I'll put this right here. You don't have to, but I'm just writing down where stuff is coming from just in case someone watching at home wants to see. So Niall already did that math for us, though. He said 20 plus -30. Is that true?
Yes.
20 plus -30 gives us -10. So that's how we could check our answer. I said it last week, but I'll say it again. One of the I love systems for so many reasons, but one of the reasons I love them is because as a student, you can literally check every single one of these. So on a test, we'll have a test, I think the end of next week. You could potentially walk away from that test knowing everything's correct if you do that little check step there. Now earlier I asked you about these equations, these nice handy equations like y equals 2, x equals 4, and you said you already know that they're not always going to look like that. So here's another system. This system, we've got y equals 3x plus 2 and 2x plus 2y equals 12. We're still going to solve this one with substitution. We said earlier, in order to use substitution, what do we need?
To have 1 point on each side, I guess. Or,
What do you mean by 1 point on each side?
well, you need to be able to replace something with a number.
Yes.
One of the variables with a number.
There you go. So do you see in our system what we could use to replace?
I guess you could do the first equation.
Yeah.
And then with that, you can put the y equals into the second equation.
Yep. So in order to use that substitution method, we're looking for x equals something or y equals something. So you're noticing that first equation there's got y equals. So we could use that to substitute into our second equation. Now what does y equal?
3x plus 2.
Yeah. It equals all of this. So sometimes students want to say, oh, y equals 3. I'm substituting 3. You can't just pick part of it. Y equals all of this. So we're going to substitute all of this in for y. When I do that, what is that going to look like?
Be like 2x
Mhm.
plus 2 parentheses,
Mhm.
3x plus 2.
Nice. Because there's multiple terms there, we need those parentheses to show I'm multiplying 2 by all of y. And then equals 12. Nice. Once we've got that, now we're in the same place as before. I've got this beautiful looking equation. What can I do?
Well, you'd start with the parentheses.
Okay.
You could distribute the 2.
Love it. What is that going to give us when we do that?
So it would be 2x plus 6x
Mm-hmm.
plus 4
Mhm.
equals 12.
Yep. Now what you want to do?
And then from there, you need to get x by itself.
Mm-hmm.
So you would, I guess you could do minus, I guess 2x.
Minus 2x.
And then, so that would go to the other side. Or, no. Because you can't,
I agree with the no, but finish that. Why can't we do that?
because you can't minus 2x.
Mm-hmm.
So,
From the 12.
from 12.
I mean, there's nothing mathematically wrong with what we just wrote, right? You could do this, but it's not helping you solve. It's just putting x on both sides now.
Oh, so would you combine like terms?
Yeah, I like that math vocab. If we combine like terms, what are we going to combine?
I guess the 2x and the 6x.
Mm-hmm.
And then would you also combine the 4 and the 12?
Let's do one at a time. So you said combine these. That's going to give me
8x.
So I'm going to write 8x. I'm just going to copy down the rest. Now you said you want to combine the 4 and the 12. How will I do that?
Or well, do you combine them? Or would you just do from there minus 4?
So subtracting 4 on both sides is combining them, right? But because they're on opposite sides of that equal sign, we can't add them together. But if we subtract 4, we get 8x equals,
8.
and then
Divide by 8.
boop.
And
And-
then x equals 1.
Okay. Final answer, x equals 1.
No.
What's wrong with that?
It's only 1/2.
Nice. So if we go back to this, I always like labeling the x and y just so I remember I need both. We got our x is 1. Y equals,
So from there, you could put the 1 into x. And you could do that with the first equation.
yeah.
So
So what I like is you've already realized the fun continues, right? We've got an extra step. Unlike before where it just said like y equals a number, we could write it over here and we're done. we're going to have to use substitution again to figure out what y is. I heard you say, let's put x equals 1 into the first equation. Could I use the second equation?
Yes. Or well,
You sound unsure, so let's do it. Let's do both. The first one here, let's start with that. You said put x equals 1 in. So it would say y equals
3 parentheses 1, which is just 3,
Mhm.
plus 2, which would give you 5.
Yep. What about the second one? So my second equation is 2x plus 2y equals 12. Here, what would it look like if I substitute x equals 1?
You would put the 1 into the x,
Mm-hmm.
which would just make it 2,
Yeah.
plus 2y equals 12. And then from there, you subtract 2 from both sides.
Mm-hmm. Which gives me
2y equals 10. And then from there, you divide 2 both sides. And that is y equals 5.
So you can probably say with more confidence now when I ask, does it matter which equation we use?
No.
No. Either equation is going to give you the same y value. We can use that to our advantage then. Notice the amount of math we had to do for this one, the amount of math we had to do for this one. So it doesn't matter, but generally you can look at the two equations and get an idea for which one's probably going to need less math, which one's going to need more. Sometimes one equation might be all positive numbers, the other one might be all negative. People tend to enjoy math problems that have positive numbers more, so you could always use that in your favor by choosing which one you think look easier, because at the end of the day, they'll give you the same answer.
Yeah.
So final answer then would be
1, x is 1, y is 5.
yeah. If we wanted to check that.
You could, I guess, use either equation, but
You could, to do like a proper check, you would want to use both. Think back to our lesson on solution points last week. Remember how we were always checking in both equations? My advice would be if you used this equation to find the answer, if you're only going to pick one equation to check with, I would choose the other equation. So if we had found 5 using this equation, I would check my point in the other one. If you use this one to find the 5, I would use the other one, just to make sure you're incorporating both equations. But to do an extra good check, you would be checking with both of them. Alternatively, I've had students in the past tell me, well, it didn't take long to do it in both, to find the 5 in both, so you could also check that way as well. Quick, a different type of check. When we say this is the solution point to this system, what does that mean?
it means if you were to graph the two equations,
Mhm.
at some point it would intersect.
Mm-hmm. At some point it would intersect at,
1 and 5.
yep. So it's just going back to what we had said a solution point is. With the substitution, we're using that part of the definition that says to be a solution point, it has to satisfy the equations. But the other part of that definition is what you just said. It means if I were to graph both of these equations, I would see those lines intersecting at this point. Nice. How do you feel about this one?
Good.
Ready to try one yourself? Where's the final answer? Looks good, but I don't know. How could we check our answer? Yep. Very nice. Okay. I've got one last one for us. The last one looks like this. Same question, what's the solution point? We've got our system of equations. What do you think we're going to do?
I guess x equals 3 plus y, but x also equals 2y minus 9.
Mm-hmm.
So I guess you could just take one of them and put them into the other one.
Mm-hmm.
So you could do 3 plus y equals 2y minus 9. Nice.
So these systems here where you've got both of them equal to x can sometimes confuse students, but you did it great. So since x equals all of this, we could use all of this to substitute for x in our other equation. Another way to think of it is if they both equal x, they both equal each other. So you're just setting these two sides equal to each other. So you said 3 plus y equals 2y minus 9. So I've got that. What do you want to do next?
I guess get y by itself.
Mm-hmm.
So you could do -3 on both sides, or -3 on both sides.
Same thing, -3 minus 3.
It would be y equals 2y minus 12.
Mm-hmm.
And then from there, would you, I guess you have to get rid of the 2y maybe?
Mm-hmm.
So,
Why not this way?
because that y is not, it doesn't have a number with it.
Yeah.
So it's just easier, I guess,
Yeah.
to do 2y.
If I subtracted y on both sides, what's that going to leave over here?
Nothing.
Exactly. So you're right, we do need to bring y to one side, but I can't get rid of this one. So I'm going to get rid of, you said the 2y. If I do that, what's that going to leave us with?
-2y, or
Over here?
yes.
How many y's is this?
Or well,
If I wanted a number here.
v1.
Mm-hmm. So 1 minus 2?
Oh, -3. Oh, so it's -1.
Mm-hmm.
-1y equals -12.
Yep. This you could also see instead of -1y, just -y. So we got -y equals -12.
And then you divide -1.
Mm-hmm. Yep. Which gives us,
Y equals 12.
yep. The way I like to think of it is -y equals -12, then y equals +12. So we've got our y equals 12. When it comes to solving this equation, you started off by subtracting 3. There are lots of different orders you can do these same steps, but I wanted to show you two. It would make it a little easier. Instead of subtracting the 2y on both sides, getting that negative, and then having to divide to make it positive, if instead of subtracting the 2y, we subtract the y, that would give you 3 equals 2y minus y, which is,
I'm thinking.
mm-hmm.
Is it? Oh, it's 1y, so it's
Mm-hmm.
just y.
Yep, y minus 9, and then to finish solving, You want to get y all by itself.
Yeah, so you would add 9 on both sides.
Yep.
Oh, okay.
And what do you know y equals?
12.
Same as down there, but fewer steps. Like I said, there's many ways to solve these and you'll end up with the same answer. We don't have to do it more than once. So either way you do it, you get y equals 12. Final answer?
No.
No.
Well, it could be because you can replace, or we can substitute y with 12.
Mm-hmm. So we've got part of our answer. You're telling me substitute y with 12. How does that help?
So when you do that, because x is by itself,
Mm-hmm.
whatever you get after you do the math on the other side is just what x equals.
So if I do that,
It'd be x equals 15.
15.
And then with that one, with the second one, it would be 2 times 12, which is 24. 24 minus 9 is 15.
Yep. So what I just saw you did was at first you figured out what x equals. And then down here you were just checking to make sure that it was right. What is the solution point then for this system?
X 15, y 12.
Yep, so we'll write that as the point, 15, 12. Nice. How are you feeling about this?
Good.
There are 2 last questions here. One of them I'm going to have you and Denise do together. And then the other one is connecting this lesson back to what you did last week with the graphing word problem. Whoop, jumping around. Okay. So this one here, I've got that system. I've got the system and I've got the graph. It's not in your notes. We've learned at this point 2 ways you can solve it. One way you can solve is by graphing, and then one way you can solve is what we were doing today with substitution. There are 2 of you and 2 methods to solving. So now we're going to let you choose. Which way would you prefer to solve that?
I'll do substitution.
Okay. Denise, that means you're going to be graphing for us.
Oh, I'm graphing?
So she's going to solve by graphing. Now, if you want to solve it by substitution, you can come up to the board. What are you expecting to see?
What are we expecting to see?
Mm-hmm. He's solving by substitution.
What are we
You're
expecting
solving-
to see, Niall? You would have me graph. Let's see, 1, 2.
Are you about to grab that? The meters.
For some reason, it makes me dizzy when I'm right up on here.
Yeah, I know what you're talking about.
You do?
I have graphed many a line of the board. It reminds me of when you go to a movie theater and you sit too close to the screen. It's hard to.
Mhm.
It's the math class version of that.
What'd you get?
Got x equals 1. And then from there, you can plug it in, so that would be the same, but it's y equals 3 minus 2, which would be y equals 1. And now with this one, do the same thing.
substitution point for the system would be,
1 and 1.
yep, just put it all together. So I caught the Niall explaining what he did. Denise, will you walk us through what you did real quick?
Okay, so when graphing this, the very
House 3 bus rider to the cafeteria, please. House 3 bus rider to the cafeteria, please.
Take it away, Denise.
Okay, so this one is here, where I started at -2 on the y and went up 3 over 1, up 3 over 1. And this one is my negative slope. So I started at 4, down 3 over 1, down 3 over 1. And this is the point that's on both lines. And so over 1, up 1. So this becomes my x and my y.
So I asked earlier what you all were expecting to see. What do you notice? You did different stuff, right?
Yeah. I don't really know what I was expecting. I just kind of started doing it.
So now that you see both of your all's work, the answer, what do you see?
I guess it's like, it seems like it will come to 1 just because there's 3 minus 2, -3 plus 4.
Oh, I see what you're saying. I'm just saying, compare what you did and what Denise did. So you both did different methods. What you get for your solution?
I'm sorry, I'm lost.
What did you get for your solution?
1 and 1.
What did Denise get for her solution?
1 and 1.
One.
So that is the solution point.
Yeah. Does it matter which method you chose to find your solution?
No,
No.
because you end up coming with the same answer either way.
Yeah. So for something like this, Denise got lucky. It was pretty easy to graph those lines since they were both already in slope-intercept form. So for one like this, I think both ways aren't too bad to do. But if the system had like fractions in it, would you have wanted to use substitution if there were a bunch of fractions everywhere?
Probably less likely to.
Yeah, I think Denise probably would have had the easier way. Denise, if you had to solve both of those, if you had to change them into slope-intercept form for graphing, it might have made it more challenging for Denise. So I'm starting to get at like why we have a couple different methods.
Yeah.
Is depending on what the system looks like, one way might be easier over the other way. There's one last part. If you want to stay at the board, you can, or if you want to sit down, it doesn't matter too much to me. But I pulled those word problems from last week up again. So remember last week we were talking about Alaska and New York. We've got, you remember from last week, those two places where we wrote equations. Last week you figured out where they had the same temperature using graphing. We're revisiting this, but now we're going to use substitution. So like I said, if you want to stay at the board, you can write it on the board. If you want to sit back down. Do you remember those equations you wrote last week?
Hardly.
I guess the question should be, do you remember how you arrived at those equations last week?
Yes. Yeah.
I think let's make sure we can agree on the equations, and then I'll have you take over with the substitution. So we've got New York, we said the average temperature was -1 degrees and is expected to rise 3 degrees per day. What was the equation we had for that?
So it would be y equals 3x minus 1.
Yep. And then I'll write it real quick. X we said was the number of days, and Y was, yep. And then in Alaska, it's 6 degrees in Alaska and expected to fall 1 degree every 2 days. What did that equation look like?
It would be y equals 1 over 2x plus
There's one thing we want to change about that.
-1.
Yep, because it's falling half a degree every day. So we saw these last week. We had done the equations last week. You solved this question last week by graphing. Instead of graphing, we are going to find which day it's the same average temperature using substitution now. Do you want to try on your paper?
Yeah.
Okay. Denise, I think you already did it, right?
I didn't show my work. I left my paper out there. Can I go get my paper, teacher?
Of course. Okay, yeah. I was trying to remember for a second when we said the answer was. I need to figure out of all these black markers which are the ones that look like this and which are the ones that look like this. Because maybe there we go. That one's better. 3x minus 1. So you're doing the right steps, right? You haven't mathematically done anything wrong. But instead of working through this with a 3.5 in the problem, there's something you can do from the beginning to get rid of the fraction. Do you remember what that something is? This goes back to like the beginning of algebra.
Can I do a decimal? No.
You could, but then you're just doing math with decimals instead of fractions. Which, I mean, some people are happier with that. If I wanted to just completely take out the fraction, the reason this is a fraction right here is because we've got 1 divided by 2. If I got rid of that divided by 2, then it wouldn't be a fraction anymore. What's the opposite of dividing by 2?
Multiply.
Yeah. So just like we can add a number on both sides, we can subtract a number on both sides, we can divide on both sides, you can multiply both sides of your equation. Here, to get rid of that fraction, I could multiply by... You do it with your finger. Yeah, 2. And over here. Whatever you do on one side, you do to the other. So here, this side isn't too bad. If I multiply that by 2, it gives me...
6x. Then the -2.
Mm-hmm. Over here, if I multiply a half by 2...
So equal -x.
Mm-hmm. You could have also multiplied by negative if you want, but really our goal was to get rid of the fraction, and you can do that just by multiplying by 2. But we get -x and then...
Plus 12.
Yep. If you're someone who's not a fan of fractions, I find this to be a real helpful step because now you're not carrying that 1/2 through as you do the rest of those steps. We could do that literally for any fraction. If this was 1/10, then we would be multiplying by 10. Even if it was something like 3/2, this had been a 3 here, multiplying by the 2 is still getting rid of that fraction. It would just be 3x instead of x. I'm going to let you take over from here. Oh yeah, you can come up. I just meant in general you can take over. But sure, finish it up for us.
It's already there. Okay.
Mm-hmm. And you can always come back up to the top if you want, if it can't all fit there.
These are better than mine, Niall.
Mm-hmm.
And then from there, you can put it into one of these.
Mm-hmm.
So you could just, so that would be 6 minus 1. So your dy equals 5.
Yep.
And then for this one, it would put it in. It would be negative x plus 6.
Not negative x, because remember you're taking out the x and replacing it with 2. With
Oh yeah, so it would just be negative 1
mm-hmm.
plus 6, which equals 5.
Yep.
So.
Now the only difference for this question is it's not just a system. We're talking about temperature and days.
So it's find the day, and if the day is x.
Yes, I love how you went back to that. Doesn't it make so much easier when we've written it down? So x is the number of days, then we figured out.
So the answer is day 2.
Day 2. Keep reading through that question. Find the day.
And what temperature it
Yeah.
is, and so that would be 5 degrees.
Yep.
So just
So on day 2, they're both 5 degrees, something like that. Perfect. Thank you so much. We feeling good about substitution?
yes.
All right. This was the last one I've got for you. Tomorrow we're going to look at the last method of solving. And that's like a 2-part lesson. So we'll do the first part tomorrow and then the second part Wednesday. And then Thursday will be the day where we pause, review everything we've learned, and really talk about like when one way is better than another way to solve. If you want to jump ahead to the homework, bye people at home.